In this paper, we introduce a novel human-drone mixed reality interface. Initially, user will align the inertial frame with the virtual inertial frame, creating a bridge between reality and the mixed reality world. Once both frames are aligned, they can be fixed using the lock keyword. After the initial setup is done, user can begin their task while the robot does its own. The user can update its current scene information using the update command, which will help to create a Voxblox representation visible in the combined map window. When robot stabilize, user call a miniaturized hologram of environment with the minimap command.
Minimap.
User draw a trajectory using an interactive green marker by selecting the task 2 option and command the robot to follow it with the publish command.
Publish.
Upon receiving the desired trajectory, the robot will start to follow it while avoiding obstacles with new planned trajectory as seen in the video. Even though user draw a trajectory through an obstacle, the robot will adjust its path to avoid collisions. Furthermore, the robot parallelly generate a map of its environment using point cloud data and transmit it in the form of mesh to the user in mixed reality, which enhances their scene awareness. You can observe both the robot's map building process and trajectory tracking in the robot Voxbox window.
Minimap.
After the robot completes its task, user can easily assign a new trajectory using an interactive marker and publish command.
Publish. Minimap.
While tracking a desired trajectory, the robot will autonomously chart a clear path while simultaneously creating a map of its surrounding. At the same time, user will continue its own task and does not require a continuous monitoring of robot. When a robot encounters an obstacle in its path, it plans a new trajectory to avoid it. However, if the user specifies an endpoint within the obstacle, the robot will halt at the nearest safe location and terminate its task, as seen in the video. Once the robot completes the user requested task, it ceases its maneuvering. To validate the effectiveness of proposed system, we compared it with industry standard human-drone interaction method, that is first-person view modality. We asked the users to explore same region but this time using FPV mode through onboard camera stream. We performed these experiments with two sets of users. To compare both the systems, we use NASA task load index method to measure the perceived effort. From presented data, it is noticeable that our proposed system has a lower global value in all the categories of TLX result. Along with TLX measurement, we also measure the area covered by each user during both the modalities. For Group 1, with experienced pilot, we measure 27% increase, while for Group 2, we measure 88% increase in the explored area covered. This enhancement in spatial awareness and reduced cognitive effort during interaction with drone highlight the effectiveness of our system.